Hi there, this is Matt Heffernan. Welcome back to my channel. This is the 10th episode in a series that seeks to demystify programming and assembly language for the 6502 family of 8-bit processors. We're using the Commander X16 as a target, as it has a 65C02 and is a particularly excellent platform for this learning process. If you haven't seen the previous episodes and need to start at the very beginning, please go back to my channel. Don't forget to subscribe and click the bell for notifications while you're there so that you'll know when the next episodes come out, and start this playlist from the beginning. So far in this series, we have learned the fundamentals of assembly programming by going through the entire 65C02 instruction set and examining how each instruction works, and then how to do basic things with the kernel and the VERA display controller. In this episode, we are going to learn about how the 65C02 and the X16 handle interrupts. We've touched on interrupts briefly before, mainly in Lesson 7, where we talked about the instructions that are used for them, like BRK and RTI. This time we were going to take a look at how to use interrupts with the X16 to control how the system reacts to hardware and take advantage of timing based on the display refresh rate. Mainly, we can think of interrupts as just being little one-shot mini-threads that pause the main thread of execution to do what they need to do, then return to let the program finish. The 65C02 supports three kinds of hardware interrupts, each triggered by a voltage level change on a pin. So if a hardware outside the CPU needs interrupts for the computer to interface with it, it will need to be tied to one of those pins. If a level change happens on pin 6, it will trigger the NMI, or non-maskable interrupt. The 65C02 is hardwired to push the program counter and status byte to the stack and jump to the address that is stored at hex address FFFA. For the X16, this means switching to ROM bank 0, as that is where the interrupt vectors are stored, and then jumping into code in the kernel ROM. The X16 ties the NMI pin to the stop key on the keyboard so that a program can be halted at any time. As a non-maskable interrupt, it means that this interrupt will happen regardless of the state of the I status bit, which is otherwise used to disable interrupts. Pin 40 is tied to the reset button on the X16 case, and that is hardwired in the CPU to jump to the address at hex FFFC. This will of course cause the system to go through a soft reset by calling the initialization code in the kernel ROM. All other interrupts go through the IRQ vector at hex FFFE, the very last 2 bytes in memory. This includes hardware interrupts tied to pin 4, as well as software interrupts triggered by the BRK instruction. The X16 ties VERA audio and video, the keyboard and mouse PS2 ports, the joystick ports, and other hardware that needs to get on the data bus at specific times. The kernel IRQ handler does a fairly large number of things, but we can still add more to it, as we will see soon. If you were to look at the last 6 bytes of the X16 kernel ROM, you would see those 3 interrupt vectors as little endian 16-bit addresses. Here is what's in the ROM for the R38 release, and these addresses are subject to change in later releases, but for now, it illustrates how it works. These vectors aren't in the other ROM banks, like the basic or monitor banks that have jump points for the kernel subroutines. Interrupts need to switch to ROM bank 0. As you can see, these addresses are all in the ROM segment of memory, so execution stays in the kernel ROM, at least initially. The NMI code simply disables IRQs with an SEI instruction, then does an indirect jump by using a RAM vector at hex 0318. At startup, this RAM vector is initialized with another ROM address for the rest of the default NMI handler, which will check the status of the stop key. You could overwrite that RAM vector with your own NMI handler, which we will see shortly. The reset vector goes to code that just stays in ROM, with no RAM vector to switch up how it works. That's probably for the best, as users want to reset to actually reset and not have some random behavior. The IRQ vector goes to code in ROM that pushes A, X, and Y to the stack, then looks 4 bytes down from the current stack pointer to look at the status byte that was pushed before jumping to the ROM vector. If the B bit was set, then this interrupt was triggered by the BRK instruction, and the default break handler will be called indirectly through a RAM vector at hex 0316. This will effectively stop your program and go straight to a basic prompt, where you could peek at the current state of RAM, which is helpful in debugging for the actual hardware. On the emulator, you could just set a breakpoint in the built-in debugger and not have to modify your code. If the B bit was clear, then this was a regular hardware IRQ. So the default IRQ handler will be called through the RAM vector at hex 0314. Both of these default handlers will end with code to pull the original register values back off the stack, then do an RTI to return to the main program thread. Because of this, it is highly recommended to save the original RAM vector value if you plan on replacing it, so you can just call it after doing your own custom break or IRQ handling. Otherwise, you will need to pull those register values back off the stack yourself and do an RTI in your custom handler to prevent your program from failing due to stack corruption. We'll see how to do the more common former approach later in this lesson. First, let's get back to that first example I promised. If you wanted to prevent the default stop handling from happening, thereby forcing the user to stop the program using your own prescribed command or doing a reset, you will need to replace the default NMI handler. First, we need to define the address of the NMI RAM vector, then a new place in RAM called default NMI to store it for later retrieval. We define a subroutine called disable NMI, which will copy the default address in the RAM vector to default NMI, then write the address for another subroutine called justRTI into the NMI RAM vector. With the new vector in place and the old one stored for safekeeping, we can return. Then we define justRTI to be simply that, just a single RTI instruction. This means that any NMI will result in simply loading up the stack, then pulling it right back out and returning to the main thread. Finally, we define one more subroutine called enable NMI, which will copy the original NMI vector address back to where it was, and default NMI handling can resume. If you were to add a custom IRQ handler, chances are it would be to process interrupts from VERA, which are controlled and monitored using 3 of its registers. By default, the VERA only has VSync interrupts enabled, which are triggered when the vertical sync signal is output to the display. That happens at a rate of 60 Hz, so you can use this interrupt as the basis of timing in your program. You can enable other interrupts using the VERA register mapped to hex 9F26, and we'll go over how those work in later episodes. For now, just be aware that VSync is enabled at startup, and generally you don't want to disable it, as that will cause the display to stop updating and pretty much everything else in the X16 will come to a crashing halt. So if you are enabling or disabling those other interrupts, make sure you keep bit 0 set to keep things humming along. You should notice that bit 7 of this register is labeled IRQ line. This is for when the line IRQ, enabled by setting bit 1, will go off. The line scan that triggers it is set by a 9-bit value, as we are dealing with a 480 line display. So bit 8 of the line number is stored there, and the lower 8 bits are stored down at hex 9F28, as you can see at the bottom of this slide. By default, the line number is 0, so this upper bit will be 0 as well. When the IRQ interrupt service routine is actually executing, the ISR register at hex 9F27 will be set to indicate what caused the IRQ. For VSync, bit 0 will be set, so you know that this IRQ happened exactly 1/60th of a second since the last time it was set. You will also see that A flow will be set unless the PCM audio FIFO is more than a quarter full. We'll get into what that means in a later video. If the SPR COL or sprite collision bit is set, then the upper nibble of this register will indicate what type of collision it was based on the collision bitmaps defined for the sprites. Again, you guessed it, that will be the topic of yet another video. For now, we're just going to concern ourselves with the VSync bit, and just check that to keep our timing straight. We will also use that to let us know that it's safe to do graphics updates, which we can do during the VSync IRQ to prevent any screen tearing from having frames only being partially rastered before a new scan begins. VERA IRQs are only useful if you actually implement a custom IRQ handler, so we'll do that right now. Like I said earlier, you still want the default IRQ handler to run, so we're just going to insert some code to be executed first by changing the IRQ RAM vector. This will be just like changing the NMI vector, except this time we are going to actually do something, and then let the default handler finish up and do the ultimate RTI. Like before, we need to define the address of the RAM vector, this time using the IRQ vector. Then we need to define the VERA ISR register address so that we can check to see which IRQs we are dealing with. Again, we need a new place label to store the original address in the RAM vector, but this time called default IRQ, and we are actually going to keep calling it. We define a subroutine called init IRQ to initialize our own IRQ handling. First, we copy the default IRQ handler address from the RAM vector to default IRQ. Then we disable IRQs with an SEI. Now it's safe to overwrite the RAM vector with the address of our own handler that we'll call custom IRQ. Then when we re-enable IRQs with a CLI and return. Once that's called, the next IRQ will jump into custom IRQ, where we first take a look at the VERA ISR register. If the vsync bit is set, we call handle vsync IRQ, and you can just imagine what it contains. Otherwise, it will go right into checking the line bit, and then calling handle line IRQ if that is set. Finally, after each bit is checked and possibly handled, we continue on to do an indirect jump using the backed up default IRQ handler address. We don't need to do an RTI here, as that will happen after the jump once the default handler is complete and gets the stack back in order. You would also want to have more code to restore the default IRQ handler to the original RAM vector before your program exits, but that would be just like the enable NMI subroutine we saw earlier. With all that knowledge, we are now ready to create a real deal useful program using interrupts, a stopwatch. We will put a simple text display on the screen with minutes, seconds, and 60 Hz ticks in decimal values separated by colons. Then we will respond to the keyboard to control the stopwatch. S will start or stop the ticks from getting counted. R will reset all the counts back to 0. And finally, Q will return us to basic. So let's get right to the editor and see how that's done. Okay, if you've seen earlier lessons, you know the drill. We get the segments set up and put in our jump start, then start our constants. We start with the IRQ RAM vector, which we are going to overwrite while our program is running. Then we have all the VERA registers we need, including the IEN and ISR registers, to make sure interrupts happen correctly. We define the bit mask for vsync that gets used for both of those registers, then finally the scale registers with the setting we will use for both of them. To get nice big numbers, we will use a scale of 32, which is a 4x zoom into the upper left corner of the display, giving us an effective 20 by 15 character display, with our 8 by 8 characters blown up to be a blocky 32 by 32. We need only 2 kernel routines, with care out to do a quick clear screen, and get in to read from the keyboard buffer. Like in our last episode, we are going to place characters onto the screen using the VERA directly to poke their screen codes into VRAM, rather than using plot and care out for moving the cursor and printing. We need to define some pesky codes, both for input and output. Luckily, the only characters we need to output are numbers and colons, and their screen codes are the same as their pesky codes. Then we need the letter keys that we are using for input, and then the CLR control code to clear the screen. Then just some generic constants to define the coordinates of our number display, which we can place here to make it easier to change where it pops up. After the constants, we can define our global variables, starting with a new vector location for the default IRQ handler. Then we have a flag for running, which will be set to 0 initially, then a non-zero value when the counters need to be ticking up. Then a byte for each place on the display, which will be binary coded decimal, or BCD values. This will make it easier to update and display them without having to do any conversion. We'll use a macro for displaying them, as we need to do the same operation for each variable. So first we want to print the number in the upper nibble, which will be the tens place. We do this by loading the whole byte into A and shifting it to the right by 4 bits. Then we OR it with the code for the 0 character to get the digit screen code. Then we store it to VERA data port 0, assuming that the address has already been set to the VRAM location it needs to go, and that the stride is 2 so that we can set up the next character without having to manually advance past the color byte. We do that by loading the whole byte again, and then using AND to zero out the upper nibble, and then doing another OR to get the screen code for the ones digit. After storing that to the next screen code position in VRAM, the macro is done. At start, we finally get to the beginning of the main thread of our program. First, we store the default IRQ handler address from the original RAM vector to the vector we set up in RAM. Then we disable interrupts while we write the address for our custom IRQ handler into the original RAM vector, so that it will get called on the next IRQ. We then make sure that the VERA is set up to generate IRQs for VSync and only VSync, and with everything all set, we can re-enable interrupts. Now we are ready to set up the display, which we do quickly by using carout to print the CLR control code, which will reset the whole screen to spaces with the current foreground and background colors. With that out of the way, we don't need to use the kernel for output anymore. We set our display scale to the value we set up above, and then zero out the running flag and all the count variables. With everything in a nice initial state, we make our first call to print display, which will show all three zeros separated by colons. This is the subroutine that will call the macro we defined above for each of the three counts, and we'll see how that works later. Now we are ready to start the main loop of our main thread. We start with the WAI to preload the stack for the next interrupt and let the CPU hang out in low power mode until the interrupt comes to wake it up. When the next instruction is executed, we know that some kind of interrupt just happened, which could have been a keystroke. So we check the keyboard buffer with a call to getIn, and if it's empty, then we can assume that the IRQ handler did all the necessary work and we go back to sleep at the top of the loop. Otherwise, we check to see what the keystroke was. If it was R, we branch to @reset. If it was S, we branch to @start-stop. If it was Q, we branch to @quit, and in any other case, we just branch back to the top of the loop and go back to sleep again. For @reset, we want to set all the counts to 0, but if a VSync interrupt happens in the middle of this, it could mess up the numbers, leaving some reset and others incremented, so we want to disable the IRQ while we zero out all three numbers and call print display again to make sure we're back to a stable state before re-enabling the interrupts. With the display ready for the next tick, we branch back to the top of the loop. An S will bring us to @start-stop, and thanks to Boolean logic, it doesn't matter whether we are running or not. We just need to flip a bit with an exclusive OR, so if the watch is stopped, running will become non-zero and the watch will start ticking. If that bit was already set, this will flip it back to clear, and running will be 0 again and the watch will stop. Once the new value is stored to running, we can go back to sleep. Finally, we get to @quit, which means that it's time to wrap up our main thread. We restore the IRQ RAM vector to its original address and then return to basic. Now we get to custom IRQ handler. This is not a subroutine, but simply a section of code that will be jumped to by the kernel at the beginning of an IRQ, thanks to our copying the address to the RAM vector. First, we check to see if the watch is running. If running is 0 after we load it, we branch to @continue, which will skip over all our custom code and jump right into the default IRQ handler in ROM. Otherwise, we load up the VERA ISR register to see if this was a VSync IRQ. We AND it to check the VSync bit, and if it's clear, we branch to @continue. Otherwise, we know that running is non-zero, and the VSync bit is set, so now it's time to do our custom IRQ handling. We start by entering decimal mode with an SED. This will change the behavior of the ADC instruction. When we load ticks into A and add 1, it will be a BCD addition rather than a binary addition. In binary mode, we would expect 9 plus 1 to be hex A, but in decimal mode, it will jump to hex 10. So while the value doesn't have the binary value of 10, it looks like 10 in hex, and we get decimal digits in each nibble. This means we will get to hex 60 after 60 ticks rather than 96 if we were in binary mode. If that hasn't happened yet, we branch ahead to @nextTick. But if ticks is at hex 60, we zero out ticks and branch ahead to @update seconds, as that value is going to need to change to roll over to the next second. If we branch to @nextTick, That means that the incremented tick value is still an A. So we store that back to the variable and skip ahead to @print, as we know that we haven't rolled over to the next second yet. If we did roll over, then it's time to increment the seconds variable, the same way we did for ticks. If the seconds haven't rolled over yet, we branch ahead to @nextSecond. Otherwise, we need to zero out seconds as well as increment the minutes. We aren't going to bother with hours here, so we'll just increment minutes the same way, but let it keep going all the way to hex 99 before it rolls back around to 0 automatically. If you want to let the stopwatch run for more than an hour, you should be able to figure out how to expand this code and add another place. Why not have a day count while you're at it? So, once the new minutes value is stored, we are ready to branch ahead to @print. If we didn't roll over the seconds, then we get to the @nextSecond, where A will still have the new seconds value, so we store it and continue on to @print. There we exit decimal mode with a CLD and call print display to show the new values. Doing this in the interrupt will give us a clean 60 frames per second on the tick counter without any tearing. Nice! Finally, we make it to @continue, where we simply do an indirect jump using the backup IRQ RAM vector to end up at the default IRQ handler in ROM, which will do all the rest of the stuff that the X16 needs to do for an IRQ, including restoring all the registers and returning from the interrupt. Most likely, this will put us back in the main loop right after the WAI, but it could have happened elsewhere in the loop, and that'll be okay. With both the main thread and the IRQ thread both defined, we finally get to their common bit of code, the print display subroutine. Since this plays with the VERA VRAM interface, it is not thread safe, which is why we disable interrupts when calling it in the main loop. We start with setting the data port to 0, then our stride to 2. Since we are assuming the default text layer at the beginning of VRAM, we can leave the bank at 0. Then we store the Y coordinate of our number display into the high byte of the VRAM address, which is the same as the row index in the default configuration. Then we set the low byte of the address to the X coordinate times 2, as we need to account for the color bytes in between the screen codes. As our stride is set to 2, we know that anything we store to data port 0 will be used as a screen code, and the color bytes will be skipped over, keeping their current values. We call our print decimal macro first with a minutes count so that it will start right at our defined X coordinate. Then we store a colon to the next slot, followed by another call to print decimal, this time using the seconds value. One more colon, then we end with one last instantiation of the print decimal macro with ticks. With all three numbers printed, we are ready to return, and that's it for this program. Of course, we have a build script, and we'll use that to assemble the stopwatch ASM into sw.prg. We can't use stopwatch.prg because that's too long for a file name if you were to use a FAT32 SD card, which limits you to an old school 8.3 file name just like MS-DOS. Also, it's fewer characters for me to type in the video, so let's get to the terminal and build it. Okay, let's call build.sh, and then we can see sw.prg in our directory listing. Let's go ahead and start the emulator. And let's get that maximized so we can see some really big numbers. Let's load sw.prg and run. Okay, now we see our zeros and colons, and our program is just waiting for some input. Let's hit S, and there we go. Our ticks are rolling over after 59, or so we presume, and our seconds start going up. And if we're a little patient, we'll see the seconds roll over and the minutes start going up. So we're about, 16, 17, 18? But yeah, you can see here these characters. They're still the same 8x8 characters. We've only zoomed into them. Of course, you could do this once you learn how to do tiles, and we'll talk about doing graphic tiles later, and you could have like really nice displays, really even looking characters, or you could simulate a 7-segment display and use all sorts of colors and just do whatever you want. But this is just a standard Petsky font, and it works pretty well for our purposes. We don't need to go through a whole lot of trouble. All right, so here we're going to 55, 56, 57, 58, 59, and there we go, rolled over to the minute. So if we hit S one more time, it pauses, and another S, it'll just pick up where it left off. If we hit R right now, well, it resets and starts back to counting immediately. So let's hit S one last time to get our final count. Okay, let's go ahead and hit Q to quit. Oh, that's a big ready. So if we just go run again, it goes back to 0 and awaits a new start. So let's hit S and let it go. Okay, now let's just hit Q while it's running. Yep, it stops. Now, if we didn't restore the original IRQ vector at the end, what do you think would have happened? If you guessed keep on going, you might have learned something today. Quitting keeps all the code in RAM, but if the custom IRQ handler was left in place, it would just keep running on its own. That means you can also use interrupts to implement background services. Pretty neat, right? Of course, the drawback is that if we were to load another program, the backed up IRQ vector could be lost, and we'd have no way to get it back other than to reset, so good citizenship would dictate to restore the vector before you quit. It would even break rerunning the Stopwatch program, as the first thing it does is back up then copy over the RAM vector, but it would just be copying the same value back on itself, and then the jump to the default handler would be right back to the top of the custom handler, meaning that we are stuck in an infinite loop inside an interrupt. Not a good place to be. So play nice, be careful, and watch your stack, and you should be all good for getting stuff done during interrupts. We got a lot more to learn in this series, and interrupts are going to be a big part going forward, especially as we deal more with graphics and sound. If you don't want to miss any episodes in the future, make sure you subscribe to my channel and click the bell to get notified when they come out. If this episode taught you anything, please click the like button. And if you have any questions, please put them in the comments, and that can influence how future episodes are made. If you can't wait for the videos to go public, become a patron and get access to new videos as soon as possible, just like the folks you see here did on my Patreon page, which you will find linked in the description, along with a GitHub repo containing all the materials for this tutorial series. Thanks for watching, and I hope to see you again soon. Bye-bye!